talk today from Mete Yücel. I forgot to ask her to say your last name. Yücel, not decent. Probably not perfect, but fairly phonetic. So yeah, I think so we'll talk about. So Mete is going to talk about the muon G-2 experiment, which is a very interesting experiment at Fermilab. Uses a very big, very strong magnet to search for new physics. So stay tuned and pay attention. It's a lot of cool stuff. Work has gone into the results that you're going to hear about. There's any announcements that we can make. So we've been doing tours for the past few weeks. This session, instead of a tour, we're going to have a panel discussion. We're calling it a muon panel. So it'll be with two people that work on two muon experiments at Fermilab. So one person that works on muon G-2, one person that works on the mu to E experiment, and we'll also have one theorist that basically works on. So you'll hear about this G-2 anomaly. So this theorist has written papers about basically building models of new physics that could explain the G-2 anomaly, and also looking at forecasting what you could do with a muon collider. So it should be interesting. You get some different perspectives, some experimental, some theoretical, to kind of fill in this picture of, what role muons have to play in particle physics. So I guess we can take a deep breath before we get started, as Brian, as is tradition. So let's all stand up and do a quick stretch. Get loose. So we're going to take 3 deep breaths together. Try and focus our minds. Set an intention to be here and learn something new. So we're just going to do 3 deep breaths. So let's take 1 deep inhale. Exhale. Wiggle your fingers, wiggle your toes. Take another deep breath in. Exhale. Get your arms over your head. Really get that body loose. Ready to learn? Let's do 1 more deep breath in. Let it out. Get going. So today we have the pleasure of having Mete with us, as I mentioned. So Mete is from Istanbul, and I'm gonna mess this up. So Istanbul it's in Turkey. I've never been there, but I've heard great things. I've heard about the Bosphorus. Yes, I would love to go. It's a great place to visit. So your PhD work was on CMS, is that right? Particle physics. And now you are a postdoc at the lab, working on muon G-2? G-2. So yes, so knows a lot about muons. Feel free to ask questions, raise your hand. We'll try and get a mic. And if we can't get a mic to them fast enough, maybe just repeat the question so the people online can. But yeah, please take it away.
Okay. Working. Welcome, everyone. So we're going to talk about muon G-2. I prepared this lecture, so the whole thing is about us trying to first, motivate this so-called G-2 anomaly, and then we're going to, as a physicist, you're not a physicist, but we're going to be in the mindset of a physicist and think about how to resolve that anomaly using scientific methods. And then, since I'm an experimentalist, the most I'm curious about is all about designing detectors, experiments, all this junction of technology with actual theoretical physics. So we will try to go from start to finish, bit by bit by adding, smaller like fundamental bits. We're going to design the mu G minus 2 experiment. So that's the idea. We're not going to get into the specifics too much. It would be, you would have to take physics or quantum physics, particle physics, all that stuff to really understand that. But like at this level, there's like a bunch of fundamental stuff that we can, get through. So we're going to get through all of those. And within this process, I'm going to, this is a conversation. I'm going to ask questions here and there. So we'll try to answer them together. Okay, let's start. Working. So it's the current magnet. We're going to talk about what the G minus 2 status is now, maybe at the end. Get this clicker going again. It was working a minute ago. Maybe I do this. Click, that's fine. Yes, sorry. Application wasn't selected. Okay, so what is particle physics? So we have this. Oops. Sorry. Okay, we have this table showing all the current particles, and the answer. Particle physics define the masses and the interactions of these fundamental particles. That makes up. So the answer, what is it? Standard model. So have you ever had like anything on the standard model so far? Because all the particle physics that we're doing, it's mostly addressing, testing the standard model and addressing the problems with the standard model. So whenever you think of particle physics, high energy physics, it's the standard model that we're testing, and it describes all the interaction within these elementary particles, and it tries to explain all these processes, but it fails from time to time. Okay, let's see the answer. Standard model. So what does it look like? So it looks like this, a mug that you can buy from a gift shop to, give it to your loved ones. Usually has this Lagrangian here, kind of summed up version of the whole theory explaining everything there is to the particle physics. But it's actually more than that. So what does it really look like? So it really looks like this. That was like a condensed, like abbreviated version of the model. So as you can see, this is quite daunting, right? So that's also one reason. I'm not a theoretical physicist, and I'm just doing experimental. Don't really want to have to deal with all these things. So it looks horrible. There's just so much part to it, and it also, when we talk about the standard model, it explains everything, but it doesn't explain gravity. It doesn't really get the general relativity and gravity into the model. So there are big problems. So this standard model, so-called standard model, doesn't actually explain everything. So so now let's talk about what types of particle physics experiments are there. So in the U.S., we kind of divide these into like 3 major frontiers. The frontiers of science. You go out there and you find new stuff. So the first one is the energy frontier. And when you think about energy frontier, you should be thinking about colliders. Okay, so there's a GIF there, 2 trucks colliding, right? That's exactly the same principle that we use when we operate the collider. So you have, for example, protons, and you make a head-on collision like those, and then you see when the tracks collide, there's all this stuff going out. So what you do, you put detectors and you try to see what's coming out. Let's say there's like this wheel coming out. You hold it and, okay, so then the track is maybe made of wheels, right? You find a piece of glass. You say, okay, this must be a piece of the track, an element that makes up the track. So that's colliders and the energy frontier. That's mostly, CERN, and there's like two big experiments there, CMS and Atlas. At Fermilab, we have a big presence on the CMS. Like a lot of physicists here work on the CMS experiment. So the other big one is the cosmic frontier. When you think about this frontier, you should be thinking about, dark matter, dark energy, telescopes. It's kind of more than that. It's not just having telescope and looking at the sky. We also have a bunch of on the ground or in the ground experiments that look for interesting phenomena for this cosmic frontier without using telescopes. So it's actually a really wide field, and Fermilab has presence in all of these experiments. Here's some like major ones. So for the G-2, though, we are in the so-called intensity frontier. That doesn't really explain much. So let me try to articulate what it's trying to say. So when we think about intensity frontier, we're thinking about rare processes and precision measurements. So it follows, the logic follows that you have rare things, you're looking for like particular things, and to get those, you need to do really precise measurements. So here the example is this like clock going about at a certain frequency that you have to find out. So you need to build your experiment to actually measure and tell the frequency of the clock. So that's, you're doing precise stuff. And, when you think about twists and clocks, that's all about precision. So here at Fermilab, we have two muon experiments. These are all, intense frontier experiments. We also have one really large compassing neutrino experiment called DUNE, not to be, misidentified as the upcoming movie. I'm not like pulling a, promo stunt here. So now we're going to talk. We're going to be talking about G-2 today. There will be a panelist from MUTE after the class, so you could ask him about, MUTE. Okay, so now let's talk about. So you're not physicists yet. You may become one day, or close to it. But we're going to use the scientific method, and we gotta get into the mindset. For that, we're going to be looking at how do we find new physics, because that's all what we're trying to do. We come to Fermilab every day, so that we test the standard model, and the only reason we do that, we want to find new physics, so we can then use that new physics elsewhere. So physics is an observational science, so you need to have an observation first. So here, you talk about gravity. And you observe, things are falling, and when you drop them, they drop to the ground. It's kind of your everyday observation. So then, what you do, you come up with a theory, right? You say maybe these have masses m1 and m2, and they're maybe attracted to each other by a force, and the proportional with the inverse of this distance square, distance between the two masses. And the proportionality between this and the force is what we call the G, right? That's something you probably know from your physics classes. And then you try to come up with an experiment, and that's kind of what we're going to do with the presentation today. This is the Henry Cavendish back in like the 1800s. They, this is a torsion pendulum, and they set up the experiment, and they confirm the theory. You have experimental data matching the theory. Yes, that's new physics. So we apply the same logic to other stuff, and since then, like 200 years passed, and there are like so many experiments, so many theories come and gone. So many steps later, okay, it's like everything adds up to another. We end up here, the picture I showed earlier, the particle physics. So this is 2016, right? The postulated Higgs particle. It was postulated like 60 years ago, but it was found in 2016. So what you have here is similar. Your observation is that you have all these particles. Now you observe the particles, you observe the interaction between the particles, and at the final moment you're saying, okay, there's like this glue particle maybe sitting at the center of it. So you postulate that particle. So we need to find it. So that's your observation. The theory that explains it is the standard model, and the experiment that finds it, EMS and Atlas at CERN. Of course, it's the experiment is much more complicated and much grander in scope compared to Cavendish's attempt finding gravitational forces, 1800s. So we're still following the same logic. So applying that logic to our class today, our lecture today, we have a new observation, and that's the anomaly in the muon gyromagnetic factor. So you probably don't know about the muon, don't know what the G factor is, you don't know what the anomaly is. So we're going to spend time explaining all of those. Okay, what is a muon? So my typical answer to this question is just a fatter electron, or you could say it's the big brother or sister of the electron. So electron is all these particles are coming from a family what we call leptons in the particle physics. Here and we kind of separate them by mass. So electron has little mass. Muon has, you can see, like 200 times mass than the electron, and the tau, the bigger brother, let's say, is even more massive. Talk about charge. So that's how electrically charged they are. So there could be positive or negative charges. Maybe you remember that from your classes. They're all -1 charge, and they have half spin, which we'll get to that in a minute. Worry about that right now. So the reason why we use muons are they're useful as discovery tools. So there's this, like when you write your theoretical model and you look at stuff, there is this mass scale that you put in usually, and like comparatively to an electron, when you use a muon, it has higher mass, and this goes with the square. You get more sensitivity to new physics. So if you want to find new physics, it's better that you use a muon. You could argue maybe it's even better to use tau. That's true, but it's even harder to work with tau. Easily produced from pion decays, so we didn't really mentioned pions or decays yet, but we'll get there as well. Relatively long time, 2.2 microseconds. Well, that doesn't really sound too long, but we're also going to discuss what lifetime is and how that really works for us in the experiment in a second. So that was the muon. So now this is the G anomaly. That's the gyromagnetic ratio, or in this case, the gyromagnetic factor. So let's try to understand that. And we're going to look at this formula here. So first, I will talk about this thing. So this mu is not the muon. I know it's the same Greek letter, confusing. This is the magnetic moment. So what is that? So let's read this. Magnetic moment is the magnetic strength of a magnetic object inside a magnetic field. So that's way too magnetic to my liking, but that's the case. You know, you have to have something magnetic. You put it in a magnetic field, and this magnetic moment is telling you how that particle is going to behave in the magnetic field. Here, I have like a muon here coming and going into the this G minus the field. So we're going to talk about these magnetic fields later. And you know, when it goes through here, you know, all this like mapped up nice field, something's going to happen. There's a question mark. So you know, the muon, the magnetic moment will tell you, you know, how that's going to behave. Another thing for this experiment that we must know is the four particles, this magnetic moment, it's in the direction of the particle spin. That's this guy. So what is this? Did you study it in your cases, or you heard about it? Anyone? No. Okay. Well, it is a really hard concept to actually talk about, because spin is a purely quantum concept. It doesn't have a classical equivalent where I can make a simple analogy, like if an apple falling down. So I use this meme to go about it that says, imagine a ball that's rotating, except it's not a ball and it's not rotating. Okay, that's what spin is. So let's talk about that for a second. We like to simplify things. So thinking a particle like a ball, spherical symmetry, that's nice. But in quantum mechanics, we know that it's not actually a ball. There's like a space that the electron occupies, but it's a distribution over all that space. So there's not actually like a real solid ball going anywhere. Just a mixture of the wave functions, right? The particle wave duality. And it's not rotating. So the idea of rotation comes from that spin is actually is an angular momentum. So you have linear momentum and then angular momentum when things rotate. So here we imagine, like, if the spin is up, it rotates this way. Spin is down, kind of goes this way. For fermion, we say this is like a plus half spin. This is like a negative half spin. But there's no actual rotation going on. So how do you tell it has angular momentum? That comes when you get these particles and put in a magnetic field. It has spin up, it's going to go rotate one way, and if it has spin down, it's going to rotate the other way. So you see them rotating. They're not actually like a ball, rotating. But kind of this analogy kind of helps visualize the things in your head. So that's what spin is. So these are kind of obvious stuff. So E is the charge. There are attractive forces between negative charges, right? The opposite charges. And the m here is the mass, and you know that already. We put those in, so I guess we kind of went through all except the g. So the g here is, so it says like gyromagnetic. So it basically ties the magnetic moment to the spin. So it's, you know, if you have spin and you're in the magnetic field, the g is going to tell the proportionality factor between these things. So you see, like, these are vectors; they're pointing at the same way, and this just gives you, it ties you this muon magnetic moment, and that's you know, something we can calculate in the theory, and that's where we see the anomaly. So what is it? So we talked about this formula. We talked about G, the proportionality constant between the spin and the magnetic moment. Shows the strength of the magnetic moment. So the prediction came in 1928. This is purely quantum mechanics. It's Dirac postulating for the electron and all spin half particles. The prediction is that G is equal to 2. Okay, you put it in there, everything works nicely. So then, of course, you know, you test this idea and you develop more theories using the scientific method we discussed earlier. 20 years passes. In that time, you know, the quantum mechanics also evolve. You have you're now stepping into the quantum field theory, kind of one step above, thinking everything, all the particles on field terms. And this is Schwinger. You know, he finds a correction to G, 2 plus alpha over pi. That's the fine constant here. So you see, you know, you're saying there are some additional effects. There are new physics. So it's actually G is actually not 2. It's G plus something, right? So that's kind of your anomaly. So then, of course, people start looking into this thing. And again, you know, many steps later, we have a prediction in the standard model for what, you know, G should be. It's this you know, ridiculous number. And we define the anomaly as, you know, we thought that's going to be 2. So, you know, you extract from 2, factorize by 2, and that's kind of your anomaly. So we know the G is, you know, different than 2. So then we set out to measure it. And, you know, standard model predicts something, but, you know, with the experiments, we find something else. So that's the tension in the anomaly. And then, as a physicist, you know, you kind of follow that and try to see if there's new physics behind it. Yeah, so let's design an experiment. Here, before we start designing, yeah, I want to say, yeah, you know, you find the anomaly and you want to find new physics. At the end, like, if you find new physics, if something that's unexplainable, then what you do, you have to come up with new theories, right? That's either an extension to the standard model or a totally new physics, like maybe supersymmetry, right? Because there's a bunch of stuff that standard model can't explain, like, you know, dark matter or the like the hierarchy problem, like why the like leptons are like the generations of families, like with electron, muon, tau. Like there's the CP violation, which is like really interesting, and why it doesn't exist in the strong sector. So it's just like when you delve into that, it's really fun stuff. So I urge you to go and, you know, find out about those things, and like each of those stuff I mentioned, they need their own lectures. So we will not be mentioning those. But like, if you find an anomaly, then we will be working on like to explain the stuff with new physics, which is Okay, so we will try to explain the anomaly. So given we know all these, so what do we know? We know this anomaly is this, so we need to find G, right? We know this magnetic moment relation to spin. So I just modified here with the anomaly because it's not one anymore. So we talked about a lot of stuff. So here is the question to you guys. So what do we need to have to make an experiment? How do we go about this? Like there are some fundamental things we need to like put it together in a basket so that we can have an experiment. So let's hear some ideas. What do we need to start doing this experiment? You have nothing. You just know about the theory. So what do you need? Okay. You need muons. True. 2 out of 2. Yes, you need a magnetic field. So the whole idea is about this magnetic moment, right? You have a magnetic particle, that's muon, and you have to put it in a magnetic field so you can measure something. That's the idea, all right? What's the third thing that we need? Okay, you're getting there. So let me give you a hint. Yeah, we have the muons, the magnetic field. It's going to do something. So but then what are we going to do, right? We have to measure it. What do we need? Something really fundamental. I suppose I didn't really mention. Maybe any other volunteer? You want to say something? Yes, you need a detector. Thank you. Yes, you have your muons. You put them in the magnetic field, and there's stuff's going to happen as they do, and then you need a detector to detect what's actually going on, measure it, and then then you have data, and then you analyze it. So we are going to talk about all these things. But before we go, there's like another trick. I mean, there's a bunch of tricks here to this experiment, of course, but this is like super fundamental to the measurement. And that, so the muon momentum and spin is, let's suppose these are aligned, okay? And the G is equal to, so this is our ring. I suppose you apply a magnetic field, so that's B, and it's shown as like this arrow coming out of the page. So that means the B is towards you. Okay, and you let the muon go. So this red arrow is the momentum, and this is spin. So these are aligned. So if G is equal to under this magnetic field, as they go around due to the magnetic field, they keep their alignment throughout this movement. So the observation is that if the G is not equal to 2, the muon momentum and the spin is not aligned. So this red and blue arrow now are not looking at the same direction under the same B, because now you set G not equal to 2. And this creates something we call precession movement. So basically, the spin starts to go around this direction axis. Here, just a gyroscope like going about around the applied magnetic field. So it starts rotating. Okay, so this will be extremely important when we're trying to find the thing, because that's kind of the effect of the anomaly. And basically, what we're trying to do is to find this frequency, omega, also called Lamarck precision frequency, with this formula. So let's talk about that for a second. At the beginning, it said, precision is frequency. We're trying to find a frequency. That's what we're trying to do in muon G minus. So we try to find the frequency of the precession, and that tells you then you have the anomaly. Okay, so we're connecting the dots. So when G is not equal to, we have this thing. So let's go about those. E is the charge. We talked about that already. We know that. M is the muon mass. Again, these are stuff that you take from the literature. You know, you or you go into school, and then get the best value you can. People already did that for us. So to make the measurement, you need to apply a magnetic field. Like that's the B, right? And we need to measure the precession frequency. So we need to measure two things actually here. Like we apply the magnetic field, but we have to know what that magnetic field is. Okay, and then we need to measure the frequency. And then if you put all those things here, you can then extract A mu, which is the muon anomaly. Okay, step one. We need muons. So we said we need muons. So where do you go to get muons? So you need 100 muons today. Where do you go? You buy them from Amazon? I don't think so. Where do you go? Yes, you need pions, but more fundamentally, like where do you get the pions then? The answer. Everyone? Well, you're kind of sitting in the answer, right? Come to. Okay, so what you need is an accelerator to make those, all those particles, the pions, protons, muons. And here at Fermilab, we produce muons. You are here, Wilson Hall. Well, I guess that's the Ramsey Auditorium. We're kind of like here on the first floor. This is the muon G minus 2 building. Like if you go out, so there's this part is kind of cut off now, so it's not open to public. But maybe in the future it will be, and maybe you'll have a chance to come and like see the experimental hall. Anyway, so that's where the muon G minus is sitting. This is the mu-T building, so that's the other muon experiment. So G minus is kind of winding down. It's finished at this point, almost finished, 99%. And so more operations are, more focus is kind of shifting to this new experiment. But I will not be talking about that. So you come to Fermilab. You could have gone to another lab. So other labs have accelerators too. You could build these in Brookhaven or Mac, or you could go to CERN. But you need an accelerator complex. For this, we're here at Fermilab. Fermilab is going to supply us with muons using the accelerator complex. So here's a GIF of that, so we're going to go through this story. Like I said, we came to Fermilab, we pay them, we need muons. The government pays them. I don't know, somehow it gets done, and then we're at the starting point of our journey. So here we have this source here, and there's this LINAC. So LINAC means a linear accelerator. So this source creates some protons, and then you, in a linear fashion, you see there's like a bunch of cubes laid one after another. They accelerate these particles, so they go. So they accelerate to 400 MeV. That's the start. After that, we have that thing called booster, the spread thing. So they go in there and they do a couple of loops. From here, the protons are accelerated to 8 GeV. So that's like an order magnitude higher. So that's compared to 400 MeV before. That's 20 times more from the LINAC. This is called a synchrotron X. And we will also talk about why that's a so once those protons are accelerated, they go into this recycler thing. So here's like a photo of it. Here, the recycler ring split this beam into 4 bunches. So, I mean, these are like really details, like too much detail at this point. But what you do, each experiment has like different beam needs. Some needs like a continuous beam. Some needs to have like these beam bunches come in with like some separation between them. So there are like a bunch of configurations that you can order here as Fermilab. So here they're split into 4 bunches as they come here. So they do that with a bunch of magnets. It comes here. That green thing is the pion production target. So that's when we produce these so-called pions. Okay. Yeah, and then those pions, when I hit the target, the pions, and then the pions will decay into muons, and those are then okay. Those muons are brought here. This blue one, the delivery ring. This delivers stuff to the muon G-2 ring, which is here, right? So when you have this beam, you have a bunch of particles in there, not just muons, but there's pions, like all this contamination. Okay, it's not a really clean-cut process. So they do use this ring to kind of circulate things and try to only get muons. You make sure that you get rid of all the other particles that you don't need. So that's the whole idea. And then they're delivered to the okay. And then we're at step 2, where we need to store the muons, and we're kind of in the G-2 territory now. Are we going to take a break, or could be later? Keep going. Yeah, it would be a good time to take a break and then continue.
So, are there any questions? Anything? We have one right here.
Can you re-explain like spin because it's not really spinning?
Oh, because
allegedly.
Okay, so the way
and there was one question on the Zoom about some of the equations. Well, maybe you could flash up there as you're explaining, like the vectors.
Yeah. Okay, let's go back to spin. Okay, I mean, this is like I said, to visualize the thing. It's a quantum concept, right? This, you have a particle, and you have this thing in the quantum mechanics. You say, okay, this guy has this spin, and this guy has that spin. How do you observe that? You observe that by taking this and put in like magnetic fields, and it's going to behave differently. The particle is going to behave according to its spin. So you can tell like which spin it is by which way the particle is like curving. So that's curvature. That tells you that it's getting an angular momentum, and that's what spin is. So this the way we explain things like this, because it's kind of easy on us. I'm going to talk about like a right-hand rule. This kind of what we use, like up and this kind of down. We will talk about that later in the magnetic field, but that's how it is. The angular momentum, spin is an angular momentum, and you see its effects by putting in a magnet.
Anyone know how an MRI machine works? Like, I mean, it's a weird concept because, well, I don't know. You think about a spinning top, it has, or I think they give an example usually on in the physics classes. You like are holding up a bike wheel and you set it rotating really quickly, and then you tilt it to a weird axis. It'll like precess. There's like some because it's rotating, it has some angular momentum. But it's hard to think of like a point-like particle as spinning, but you see a similar effect with electrons, or like an MRI machine basically works by applying a magnetic field, and that lines up all the water molecules, has some intrinsic spin. So it lines up the spins of those water molecules and then pulses them. And so different tissues, your bones will react differently. The spins in different materials will react differently. And so that's how you can, like, an MRI machine works.
That's really great. I'm going to show you, because there's a slide that I put in the extra. I wasn't sure about talking about this. It's like really cool. So, okay, so like that's a particle, but this atoms have spin as well, and like all these materials, magnetic materials, they do have. So when you look at a material, they have like domains called domains. They have like different spins, like they each all like looking at different angles. So like this part is like looking this way, this part is looking this way, and when you go into like an MRI, have an external field. So you put yourself or this object in an external field, a strong field, and then what happens? That they orient, right? And kind of what MRI does is then it's measure when the magnetic field is off, they go back. So it's all angular momentum and the interaction with the magnetic field. And you do create some ferromagnets like this. You put it in a strong magnetic field. They all align one way, and then when you take out the external field, they stay that way. They stay aligned, and that's like a powerful magnet that you create. Let's show you that. A reason to show that.
Yeah, so MRI, you line up all the spins, and then you like say you turn off the field, they measure like the relaxation time for them to like settle back into different orientation. But yeah, particles have spins. It's a weird concept when you first learn it, but it has enabled a lot of cool measurement techniques and physics experiments as well. We have one question from the Zoom, which I think is very fundamental. Are muons present in all subatomic particles? So I guess, what is a muon? I don't know if you have a standard model diagram or.
Let's go back to the diagram. It's back. Okay, so when we look at the muon is here. So when we talk about this, we're saying these are elementary particles, meaning they don't have any other inner structure. So here we have the muon, electrons. These are leptons. These are quarks. There are like 6 of them. There's neutrinos that we haven't talked about. It's really cool thing. The Dune experiment that I mentioned. They're trying to measure the masses of these neutrinos. Why I'm talking about this? Because these are elementary, so they don't have any internal structure. All the other like composite stuff, like a proton or an atom, it's just they're made up from these elementary particles. So when we talk about a muon, it doesn't have like any other like smaller particle in it.
We're going to get started again. Hope you had a nice break. I tried to answer some questions that popped up in the chat, but I think we can go ahead. We got to figure out how are we going to store these muons. So yeah, you can take it away.
Okay. So after the break, I'm totally lost, so you have to help me. So where are we? So, okay, we need to store the muons. So we have the muons. We need to store them so we can study them. That's easy as that. Like take them, put them in a bottle. So here we need to discuss a few things that you don't know. Muon decay. So these particles, either they're like elementary particle or composite particles. Most of them are not like stable particles, so they don't live forever. They do decay. So they release some energy, and they decay into decay products, which is like other particles, right? So here in this muon's case, it decays into an electron. It's sibling. And it also releases some neutrinos, those pesky neutrinos we talked about earlier. Standard model does not come up with the masses for these, but we know now, thanks to new experiments and theories, that they do possess neutrinos. So like an experiment like Dune is trying to measure those neutrino masses. Anyway, side information. This decay happens. You see, this is the G-2 data, the actual data from the detector. You plot it, you can actually see that a decrease in the population muons due to decay, because they decay and they cease to be muons. And from here, from this curve, the exponential curve, you can actually get a lifetime. So that's what you say when you say the muon lifetime is 64 microseconds. But wait a minute, we said muon lifetime was 2 microseconds. But then when we measure it, it's 64. So there must be something wrong here. So can anyone tell me why that is? And, like we know that's 2 microseconds, but in the lab, like when we measured, it's 64. Why could that be? Maybe you remember the quantum mechanics class you took? Broke?
Got a lecture about this.
Oh, machine broke. Yeah. Well, okay.
Take a guess.
Yes. Yes. So you're right on the money. So this is due to special relativity. The picture of Einstein here. So when you go into quantum mechanics, you learn all these like interesting things. If you watched Nolan movie, what was Interstellar? Like that's all about this kind of. Good that people make movies about physicists. We look cooler here. So when you put in that you put in the relativity, then you see that things are changing. The distances and the time actually changes if you're operating at light speed. So that's what it means. So let's calculate the distance traveled by the muon. So it lives for 64 microseconds. It's a relativistic particle. So then it goes like 20 kilometers. That means if you want to store these muons, what do? Like, do you build like a 20-kilometer tunnel? No, we don't build that, right? What do we do then? Well, I mean, you already saw the magnet. There's the alternative. What is the alternative to linear section? Yeah. Circle, yes. So we need to come up with a circular design. Previously, we talked about accelerating the protons, right? There was like this booster and other things, so they all look like circles. And that's why, because when you go to this relativistic speeds, we can't just do this linearly. So when you have a circular design, you can just keep looping them until you get what you need. For the stored muons, we need then like a radial section of a tube, just a circle. That's what we need. So another thing is to store the muons. So when like they come into this thing, like they're all over the place. So we don't like that because like when they start to rotate, they're like dispersed like that. They're going to hit stuff like they're going to hit the walls. They're going to hit like other stuff that we put in into the storage area, and they're going to disappear on us. So we don't want that. We need focusing. So that's pretty fundamental too for like beam dynamics. So let's say this is the vertical axis. This is the radial axis. We need focusing on both. So when we do that, you focus these things, I kind of push them all into the middle. So they're like a nice little bunch at the center. So that way we can store them longer. They're not like escaping. Okay, you really want them in the middle of your storage ring. And to do that, we're going to need magnets and make this thing turn. So where can we buy a magnet or find a magnet, construct ourselves? Like, how do you go about that? Let's hear some ideas. mu on G minus the magnet. It's a huge magnet. How do we get to that? We know we came to Fermilab to get the muon, so where do we go to get a magnet? Any ideas? Well, so okay, for those of you who wants to be engineers, the first thing, like each project, you want to ask yourself is that, can I buy it off the shelf? Okay, you don't want to invent new things. First, you need to look up for existing technology. And a magnet like this actually exists, okay? Because it was sitting in the Brookhaven lab. So I talked about, you can get off the shelf. You can get off the shelf this magnet because, you know, all this muon anomaly, it's going way past. And CERN had an experiment, then Brookhaven had an experiment. And, you know, the guys from Fermilab, they're like, okay, we'll take the magnets from the Brookhaven, come here, and make a better experiment. So then you don't have to really worry about the magnet. So it's a huge magnet. It's 50 feet in diameter, like 50 tons. And Brookhaven, if you don't know, is in Brookhaven, New York. It's far away. And we put it on a truck, first on a ship, I suppose, and go through the East Coast, come through the Florida, 50-ton thing. Yeah, that's like next to Bahamas. Come here, make landing here. I guess that's Florida or Alabama. Anyway, and then goes through this, you know, highway up till here, Chicago, and this you know, really precise magnet, like really leveled nicely and delivered to the Fermilab. That's, you know, something amazing that happened I mean, it's delivered here in 2014. So I kind of joined the experiment maybe like 3 years later. So it was even like before my time. I'm not sure if anyone was here.
Why didn't they just drive it across through Pennsylvania?
That's a typical question, right? So why don't let's hear some answers. You know it already?
The magnet couldn't be bent, so by taking it around Florida and up the Mississippi, the water would prevent damage to the magnet, so that could be usable when it arrives at Fermilab.
Very complicated answer. The real answer is that they couldn't, like the roads aren't wide enough to get it through. You just can't take the shortest route. I mean, you should get the shortest route. What they come up with.
Is it on? All right. This isn't really about how they like why they brought it around the water, but like, how did Brookhaven get such big magnets?
Oh, I mean, obviously, they didn't buy off the shelf. They had to do it themselves. I mean, they, of course, now there are companies that specializes on building superconducting magnets. So they built this like really specific, this really nice magnet for them. The real question is, actually, you should have asked, why didn't they do in Brookhaven? Why do we need all this, right? And that's a complicated question to answer, but this usually comes down to the cost and kind of the strategy of the lab. So Brookhaven kind of let go the muon physics, and kind of Fermilab picked it up.
Was the magnet used for a previous experiment?
Yeah, this was used in the previous G-6 experiment, and we will talk about that. Okay, so so we were talking about superconducting solenoids. So this is how it looks, how it looked before actually, this blue thing. So now we put some insulation on top to kind of, you know, control the temperature of the magnet. Also, you know, people kept dropping their like keys on top of the magnet, so we didn't want to have that. Again, funny tidbit, I think this person here is among us sitting there, one of our panelists, Jason. That's you, right? That's him. So you're really going, yeah, no, that's you. You have the same green thing on you. Like you're literally unchanged. Anyway, so we have a great panelist there. He's going to know all about the history of G-. Anyway, so this, what's the superconducting solenoid? It produces 1.45 Tesla magnetic field. So create a solenoid to create magnetic field. The way you do that.
Can you explain how strong 1.45 Tesla
Yes,
is compared to like the Earth's magnetic field? Maybe?
I would like to do that. So 1.45 Tesla is bigger than Earth's magnetic field by 30,000 times. That's a lot of times. Some random magnet facts. If you go to an MRI, you experience a similar magnetic field between 1 to 3 Teslas. So that you feel like, if you want to feel it, what it feels like, you can just go, take an MRI. The strongest magnet, I think they're built in China, it's like 45 Tesla or something. So, but this is a super precise thing, and it's large. An MRI magnet is smaller in comparison. So go and get those MRIs in after this. So create a magnet, you basically take a wire, okay, so conductor, you loop it around, and then you put charge, a battery, right? So this information here. So as the current goes through, the electrons going through the wire, so they have to be moving. They induct a magnetic field, like so, inside here, inside this so-called solenoid. So that's why it's like a cylindrical structure. You could do like a torus and some other shapes too. But you need this current going through. And the direction of the magnetic field is usually easily determined by this right-hand rule. So you kind of, with your 4 fingers, your hand, you follow the direction of the current. Like, you loop the wire, so you're kind of grabbing the wire. So as you do that, your thumb indicates the direction magnetic field, as shown here. A superconducting magnet is a solenoid that has a 0 resistance. So some materials, when you cool them enough, they don't have any resistance. And when you don't have any resistance, then you can conduct like really large currents. And that's good for us, because then you can create large magnetic fields that we can use in this experiment or like in the industry. Means stronger magnetic fields. So here's that magnetic field. I mean, this is the G- ring from it's a cross section of the ring. That's the yoke. These are the coils. There's like 4 set of coils here, 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 here. And this is the magnetic field that is creating this, our magnet. That's the muon coming through the ring. And this is the force, the magnetic field exerting on the muon, so that muon feels this force, and then it starts to rotate. So it starts rotating in the storage ring, right? So if you use the magnetic field to do the radial focusing, so that means now we need to do the vertical focusing. But there are some.
Can you show that one more time? Are you all familiar with what the circle dot, and the circle cross means? This is that's a no. So basically, this is how they document. In this case, what this would be current going in one direction. So this means it's coming out of the page. I mean, we draw things on 2 dimensions, but really we're trying to model three-dimensional systems, right? So this circle with the dot means there's something coming out of the page, and this circle with an X means something going into the page. And a lot of the right-hand rule is basically because a lot of the math when you do this has to do with cross products, which you probably maybe learn in math at some point. But So it's important to, the way I remembered it when I was in school was I would think about an arrow, like, you know, if it's coming right at me, you see the point. If it's going away from me, you'd see like, you know, like the bushy X thing. But anyways, but that's just what that notation means. And moving charge in general creates a magnetic field. So if you know, move electrons in this direction, in this, you know, you'll create that magnetic field. Anyways, just making sure you understand.
Is that more clear now? Yes, what the that's what the I was talking about. There are like more tricks. So this is kind of like details, but it's fun to talk about them. The first of all, like this injection. So I see that this is like so this is the beam line. So the muons are coming through here, and they're entering this storage ring. But you know, this ring has like magnetic fields everywhere. So as they come in, they actually are affected by the magnetic field of the ring, and then they're kind of they're rejected from their like intended orbit. So how do we correct the injection orbits? So use what can we use to correct this magnetic field? The answer is actually on the page. Use another magnet. Okay. So you know, think about manipulating beam. You know, you always, you know, think in terms of magnet. So there's this, you know, this outside field to kind of minimize that and have like a good entryway for the muons into the storage ring. You put this like little inflector magnet. So they kind of come in the inflector and they kind of inflect, and then they go into the orbit. But like if we study this orbit, this injection orbit, simulate it, for example, you see that's not really in the center. So that's how the calculation works. We want to really put them into center, because otherwise, you know, we're going to lose the muons. Instead, you know, we need them in the center. So the beam magnetic field makes the radial focusing, but they're not in the right orbit yet. So we need another magnet. We need more magnets actually kick the muons into the correct orbit. So this kicker, so-called kickers, are actually kicking the muon, but they're not like in a I don't know, in a physical term that you're associated with. They're kicking it magnetically, right? Because these are another like set of magnets that's really high power magnets. They kick. So the kick, you know, terminology comes from they operate for a really short amount of time. They pull a large current that changes the magnetic field. So you know, give them a magnetic kick, and you put all these muons into the right orbit. So from this purple circle, you go into the red circle. And if you see, you observe here, the red circle is kind of in the center. So that's how the actual radial focusing is established with this super kicker magnet. So how about vertical focusing? For vertical focusing, instead of magnets, we use electrostatic plates. These are called quadrupoles. So basically what they do, so there's like 4 of them. Now we have this long plate here. These are positively charged. These are negatively charged. Maybe if you remember from your physics classes, you could draw these electric field lines from like positive charges to negative, right? And then it creates the electrical field like so. So if you have this, you know, muon here, like kind of on the outside, going its way, if you're here, yeah, you're going to feel this electric field, and it will push the muon into the. That's the vertical focusing. And with this, muons are stored because we have the rate. Yes. Yes, this is the Fermilab logo. That's right. Oh, it's here somewhere. But that's there. Okay, exactly. You know, I'll use that. I'll use that next time. Anyway, with the Fermilab logo established, they're stored. Okay, we have radial and vertical focus. Yeah, this beam dynamics is big at Fermilab. So, I mean, actually, you want these electrostatic quadrupoles like all the way, like always on, but you can't have it. I have only 4 of them, like here. Reason, the answers. But the reason is because, you know, there's other stuff there. Like we need to put detectors and other like components going in there. So it's just you can't really have them like here like all the way. But you know that would be like that would be better. Anyway, so we established the focusing. If you remember, like from the earlier, we need to measure the frequency and the magnetic field. So here we are at the point where we measure the magnetic field. To do that, we use something called this NMR probe, nuclear magnetic resonance probe. I'm not going to get into details how these work, but we kind of, you know, talk about with the MRI machines and how they work, kind of similar. So we have these tubes, and these basically measure magnetic field. So we have this ring, and we want to measure the magnetic field. So and we have these probes. So for all you know now about like storing the muons and everything, where should we place these probes? Inside the storage region or outside the storage region? What makes more sense? There's some answers. We have 2 choices.
Any guesses? Oh, should I guess? Want to guess? Want to save me
Everyone's on the edge.
Inside the storage region?
That would be wrong.
Straight off, right? You probably get a more direct measurement inside, but it might mess up.
That's good. Are you a physicist or something? So if you put them inside, you're putting them into the storage region, right? And what we said, like, we don't want anything in the storage region. We just want muon like in the middle. So as you put stuff into the storage region, they're going to interact with the beam, and then you're going to lose your muons. And you know, they're going to like interact, and all these other particles will come out. So there's always a trade-off between like putting stuff into the ring. So you'll put them outside the storage region. The next question is, how many should we place? It's a really hard question, but it has a simple answer. Yes, correct. Right? Yeah, all of them. We put all of them. Okay. So that's we really have a nice magnetic field measurement in this experiment, thanks to this NMR probe. So this kind of like the upper layer, and this is like below the ring. There's a bunch of them here. It's all over the place. They're constantly monitoring what the magnetic field is. So that's how you get a really good magnetic field. But that's not really the case, because we still want to know what the magnetic field inside the region, the actual field felt by the muons. How can we measure inside of the storage region? Any ideas? Let's be creative here.
We use the detectors to like measure the spin of the muons, then doesn't that
But yeah, that's kind of what we're doing with the probes. But yeah, so how do we do that in the storage region? This I bet you know you can't answer this question like correctly. So let me you know not tease you any longer and give you the answer. We actually use the same things, you know, these NMR probes, but we put them on a trolley. How easy is that, right? So the idea is, you know, when the muons are not there, you have these tracks built in, these rails. You put your little trolley there, and you ride it like across the the whole storage ring, and it carries these NMR probes. And that actually, like, here's a trolley with a bunch of probes in there, and then it just actually goes in there and actually measures the magnetic field inside the region. So obviously, this experiment ran for like years, right? Since 2017. So we do this all the time. Like whenever we're not running muons, we get the trolley out, put it inside the ring, and then measure the magnetic field and take it out, because when the muon comes, you don't want anything in front of the beam. So that's kind of how we do the inside magnetic field measurement, which is really important. Anyway, so as trolley moves, it makes these maps, and then kind of combine that into this magnetic field that's inside the storage ring. It just goes around.
What does ppm mean?
Oh, we'll get there. Number. We'll get. Okay, step 3. We need detectors. So so we have now the magnet. They're turning. They're stored. We did all these tricks with NMR probes and measuring the field and making them stay in the ring. So now we need detectors, the last step, to detect them. What are we trying to measure? Anyone remember? It's been so long we talked about it. Yes. Kind of correct. We're looking at spin, and it's a precession frequency. Like we said, we were looking for a frequency. How do we detect muon spin precessing? So I mean that's a harder question by muon decay product. So muons will be rotating, right? They will be spinning. They will be precessing. So muons also are not like stable particles. They're elementary, but they're not stable. They're going to decay into electrons. In this case, it's a positive muon, so it's going to decay into a positron, which is the electron with a positive charge. So as it decays, with this precision movement, there will be positrons, and we could put detectors like around this ring to measure those positrons. And here is the whole idea, which I need to give you. I need to tell you. We kind of talked about this before, but what you need to know is that muon decay, this decaying positrons, happens in the direction of the muon spin. So we were talking about determining the frequency of the spin precessing, right? And we do that by positrons. We could tell that because the positrons will be emitted like along those lines. What do I mean? So so this is like a cartoon that I prepared. It's not like a real physics simulation, just to illustrate. So let's imagine like this is our ring, and these are our detectors. I put a bunch of detectors around. So we're like, as a physicist, we don't have everything yet, so we're just like simulating, right? We go into write code and just see what could be happening, like if I put these detectors in. So here, this arrow notation we already explained. The B field is coming out of the page towards you. Here's a really large muon. They're not as large in real life. And this momentum, and so this is the momentum direction. It's going like this, and this is its spin. The blue is the spin, and it will be like the positrons will be the red balls that will be emitted from the large muon. So let's see what happens when the G is equal to. So here our muon is rotating. Since G is equal to, there's no precession movement, meaning the spin, the blue arrow and the red arrow are in the same direction. They're aligned, and you can see that there's a bunch of stuff coming out of the muon. Those are the positrons, like really rapidly, and due to the magnetic field, when they're emitted, they're curved, and they hit the detectors. So I put the detectors in a good place, right, in the inside of the ring. So the positrons emitted, they hit the detectors, and what you will see here without the anomaly, you'll just see, like if you look at these detectors, you'll see a flat distribution of positrons coming into these detectors. But there is the anomaly, and things will change. So let's see about that. Okay, so now the G will not be equal to, so the spin will presses. Let's see how that works. Okay, so this is going to be more difficult to understand, but see that spin direction, this blue arrow, it started processing. When it's processing, so I kind of slow it down, so it's easier to see. You have all these positrons going everywhere now. Okay, they're not as easily identifiable as the previous version. So here, what you see, and this is the whole idea. The whole idea, the money shot of the experiment, if spin is processing, and we learned that the positrons, the decay products, are emitted in the spin direction, right? The whole idea is that when that spin is towards the detectors, you get more counts. When that spin is looking away, you get less counts in the detectors. You could kind of observe that here because, like, if you look at when the blue arrow is like looking outwards, some of the positrons will not hit the detectors. So when the spin is looking through the detectors, you'll get more counts. When the spin is looking away, you get less counts. All right, so it will be a frequency, and that frequency will tell you about the anomaly. So that's the whole basis. I just like let it run, and hopefully, that's interesting. At least. Okay, so I will move on. If there isn't any questions.
I want to stress how fast, I guess, these oscillations. So this is the whole graph is 1 microsecond. 100 microseconds, okay. But I guess you're able to resolve the wiggles at very fine time scales. These calorimeters are very fast detectors, And I was just going to say, well, when you talk about food, you talk about calories. It's a unit of energy. So it's like calorimeter. It's like it measures energy is basically what a calorimeter does. Um, very fast, and they're able to measure the whole energy of the positron that comes out.
Okay. Okay, they add a storage ring. They are more precise now. So this is 270 parts per million, not parts per thousand. And I'm going to talk what those means in a second. Bear with me. The third measurement, storage ring, plus the electrostatic quadrupoles, the vertical focusing we talked about. That's 7 ppm. That's the error is getting smaller and smaller. So then Brookhaven took the effort, right? And they built this magnet and did the same experiment. They had a storage ring, a magnet, the one we saw, the electrostatic quadrupoles, kickers, and 24 calorimeters. So this ends up being 14 improvement on the CERN measurement. That's like 0.5 parts per million error on the measurement. So when we decided to do this at Fermilab, we said, we have to do one better, right? We need a more precise measurement and see if that there's an actual anomaly. So we need improvements. So now we're going to talk about those improvements to reach this 0.1 ppm target figure. And so what does 0.1 ppm look like? So since I always said, we're measuring frequencies, I kind of prepared this like cartoons to illustrate like the visual differences. When it's visual, it's maybe easier to like grasp. So this is 0.1%. So we have like two like sinusoidal waves, and the difference in the frequency is like 1/1000th, right? Sorry, 1/10. So this is like easily visible. If I like play it, as these waves go around, you could really see. You can really separate the two wave functions just visually. Did we switch?
Well, I'll probably do that for the question.
Yeah, that's.
I think, yeah, sounds good.
Sorry, technical problems.
I knew that battery might die, but I risked it. Carry on.
Well, we are risk takers at Fermilab, so that's up. So now 1 part per thousand. So this is 1 per thousand. So when you make a 1 per thousand error in your measurement. So I'm just going to play this. Okay, so as you can see, it's going. As I've kind of slowed it down, of course, so we can see it easier. So you can't really see anything. So it's 2 times zoom, and you don't really get to see anything. It's like the blue. Like currently, you only can only tell like there's one thing. There isn't an anomaly, right? 10 times zoom. This is kind of you're on your phone, you're zooming. That crime show that you're watching, it's just like zoom here, and you kind of see the details. You kind of see the precision. So with the 1 per thousand, we do get 100 zoom, and we kind of see now that they're separate. But like previously, you had no idea. They were just like the same picture. So the same thing, but this is 1 part per million. Okay. So let's play that. So this is like 0.0001%. So they're the same picture. So now I'm going to zoom, but I'm going to zoom even, faster, like 100 zoom. You zoom in like 100 times, same picture, right? You zoom 1,000 times, it's the same picture. This kind of gives you this scale. So you zoom for like 100,000 times, and then you can actually see like there's some stuff going on. So that's kind of give you the scale for, let me talk about this like ppms, this error bars of what this is. And this is just 1 part per million. With the experiment, we're trying to do 10 times better than this. So to do this experiment better at Fermilab, as physicists, we're going to put our detective hats. And this is like really scary 2 tables on the screen here. But then we're not going into details. But what we're going to do with our detective hats on, we're going to see where we can improve. Because that's like what physicists do. So we're doing the same, like a similar experiment. What could we be improving? Okay. So when you look at it, these statistics, runs, and then some errors that they're reporting here in the ppm level, you see that, for example, that this CBO thing seems to be a problem. So you see, okay, that number is big compared to the other numbers. So I'll try to innovate and maybe make that error smaller. Okay, so these are all called systematics. So when you do an experiment, there are errors associated with that. Usually, depends on the technique or the equipment used. So as the technology evolves, you can actually make them smaller by being clever, actually. So what is the CBO thing? So another thing I mentioned. So yeah, we put them in the storage ring in the center, but actually they're kind of wobbling. Okay, this is called the CBO effect. And this dashed line is the ideal orbit, but this blue one is the actual orbit. And this is called the coherent Betatron oscillation. So due to this, this is, of course, you don't have the perfect magnetic field. They're kind of not following the right orbit, and they kind of end up, do not end up in the same place. So that's if they would, it will be like a closed loop. And due to this, you have errors, you lost muons, and whatnot. So this necessitates, and it's like a fundamental improvement to the G-2 from Brookhaven. We need a better description of the beam. Okay, we don't really get to do that with the old G-2 because, like with the colorimeters, I showed you the plot. It's going up and down. Okay, but in reality, you don't really know where that muon or the positron is coming from. Let's take this example. So muon is going, and it can decay at any moment. So like if it decays here, this positron, maybe it curls and comes here. Here's the calorimeter. But maybe it decayed here, and this positron came all the way down here and hit the same calorimeter. So you see those ups and downs, but you don't really know where the muon actually decayed. Okay, you don't really know your beam dynamics well. You don't know your beam well. So what we know, we want to know where the positron came from and have a better description of the beam. So to do that, we used something called tracking. So this trackers, so-called, like they exist in every particle physics experiments almost. So this their goal is to determine the tracks left by these particles. In our case, these are a straw tracker. These are actual made out of actual drinking straws by a drinking company, and they're obviously thinner than our regular straws, so that like when a positron passes, it doesn't leave like all of its energy, so it doesn't disturb and destroy the positron. So as it goes through these things, it leaves a trace, and that enables us to get a profile of the beam at the center of the ring. This is how it works. Like, this is the same picture. So we added these trackers now, these pieces in front of the colorimeter. So that means like a positron comes through, it's going to hit a bunch of straws. So you have the first straw, the second straw, the third straw, the fourth straw. And you have that signal, and then you can then reconstruct back. So you can say, okay, I hit here, hit here, hit here, hit here, and then you trace this back. It's called reconstruction. And then you can actually trace it back to its originator, okay? And that's where the muon decayed into a positron. So with that, we actually have more information on how the beam behaves. Okay, I went through all the like major components to the experiment. So a fun thing we do is that we take our trolley and we put a camera on it, okay? And then we let it go in the ring, and we do take a video of the ring. So I'm going to show you what's inside the ring. And we've already talked about the colorimeters, trackers, kickers, and everything. And I'm going to just show you those. This trolley doesn't really go for speed. It's like a really slow vehicle. So this whole thing is like cut and kind of set up, okay? So let's go. Kind of jerky movement, normal. This is the trackers. So if you decay, you're like curving here into a detector, and you pass through these trackers. And here's the colorimeter there at the back. So these are the quad plates, this to make the vertical focusing. There's a bunch of long plates, as you can see, on 4 sides, positive charged and negatively charged. Okay, there's a cut here. Quads, more quads. Okay, again, plates. Like these are, you see how long they are. And these are kickers. So these are actually called bazookas. So there's like boom, and they put the muons in the right orbit. So there are 3 of them. Quads again. Okay. So I guess we see that trackers kind of get a glimpse of the colorimeter, and we all see all the quadrupoles and the kickers. And that's kind of the trolley kind of goes to the sides and to the trolley garage, and then you can take the trolley out. So now it's not in front of the beam, so we can do the experiment. Okay, with all these improvements and with the tracking, we can actually get a view of the beam. So this is again real experimental data, and this is how the beam looks. Let's play that. So as you can see, that's the CBO motion, and it's just like this whole thing. It's centered, but it's not really stable, right? It has that wobbly motion. This is radial. This is vertical. You look at a cross section of that storage ring, and you can see that the mean. So this is the mean of this distribution, and this is the kind of the error on the distribution, like the deviation. And you see that as time goes on, the muons decay as they circle around the storage ring, so that the population gets smaller and smaller. But with that, we have a nice description of the beam, and that's like one major way we improve on the previous experiment and like get better results. Okay, and the discovery. So let me check time here. How am I doing? I'm almost out of time. You have to bear with me. Anyway, so we found B. We measured it. We measured the frequency, with all the colorimeters and all the improvements. We have this wiggly figure, and from there we get the frequency. So we put those in there, and then we calculate the anomaly, like so. We put them on a chart. This is the old experiment. These are the final experiment. So there are a bunch of runs. So there are like 6 runs in total for our G-2 experiment. we analyzed so far run 1 and run 2 and run 3. And currently we're analyzing the last bit of data, the last runs, run 4, 5, and 6. And with that, there's going to be more statistics coming in. So this like kind of average it, and this is what you give to the press. Like this is the anomaly with this like error bars. This is usually a plot that we don't like to show because there's a bunch of controversy. But what you do is that you have your average and you compare it to the standard model value, right? We talk about the anomaly, and you kind of then you give that some in the units of something called standard deviation. So this differs from the standard model prediction by 5 sigma, they say. So sigma is the standard deviation. So that, of course, doesn't mean anything to you, but I'm going to talk about that as well. So it's the last frontier. So to understand, this is the final thing for the statistics and the sigma difference. So we talked about the systematic errors. That's due to like the equipment and the measurement technique and whatever. But this whole thing is also based on statistics. So the idea is that the more statistics you gather, right, for your experiment, and this is true for any experiment, you get less errors. You know, you get to be more precise. So here I will just, this again, funky simulation, just a toy Monte Carlo, showing you some measurements. So I have the measurement blue, and I'm adding events. So there's 4 events. Now there's 5 events. And you calculate the mean each time. Okay, it just jumps around because you don't have enough statistics. You only have so many events. Okay, so it just jumps around. You really at this point don't know what the actual value is. You're doing experiments, but you're repeating them, right? You're getting different results, but they culminate in a distribution. They will eventually. So it's going around. It doesn't really look like fitting any distribution. So if you like put it like a normal, if I try to like fit a normal distribution here, maybe you saw that in your physics class. I'm not sure, but you could describe this distribution in 2 ways. You give it its mean. The mean is basically the average point of these distributed values. And then you give something like a standard deviation. So standard deviation tells you how is your distribution, how wide your distribution is, like how far away from your mean value your distribution. How large? If it's a large standard deviation, like a large, it's a wide distribution. It's smaller. It gets smaller. So and finally, so you have this distribution, right? That's kind of coming into place, but it doesn't really look like anything. It's just like all over the place. You look at the standard model, right? You're comparing your number to the standard model. That's this green line, and like you calculate the standard deviation, and you basically look at how many standard deviations you're away from this standard model number. Basically, measure this distance, right? It's your measurement. And it's bad. Like the separation here, I say it's like 1.6 sigma. So this means like it's not good enough for a physics result. It says, your measurement could be the standard model. I mean, it's within error. Okay, these are kind of overlapping. Like look at this distribution that I fitting here. It's overlapping the standard model value quite a bit. You see the crossing there. So this is not good enough. So other than like solving the systematic errors, we need to deal with the statistical errors. And the only way to do that, just to get more muons, like more statistics, more muons. And that's why also we came to Fermilab, right? Because they can produce like more muons, they can deliver more muons. With all the improvements, we can store more muons. And that all, culminates into having more statistics. That's going to decrease our error. So let's see that. So let me play this. So there's like hundreds of thousands of events, the same toy Monte Carlo, and get a nice distribution. The expected value and their measurements kind of right on. and you are no way over the standard model prediction, and then you say, okay, I'm like 5 sigma away. You know, you kind of, again, make the same measurements. You're not overlapping. It's kind of like a visual representation of what we're doing. And then you come back to this plot and say, yeah, like our measurement is 5 sigma away from this white paper. And that 5 sigma is significant. That's usually when we claim we have enough statistic and confidence in our data to make an announcement. Like, we did find something new. Like, if you repeat this experiment with confidence, you're going to still, with 99.9 confidence, you're still going to find the same value. So we found something. It's controversial because the current standard model prediction from the theory groups are not clear yet. So if the tension is going to get smaller or bigger, we currently don't know, but that makes it really exciting. So finally, this had like big impact on the media. Here's the New York Times article from the first run. Particles, tiny wobble. Yeah, it's a nice word to use. Here's the second run. So the second paper, where we had all these run 1, 2, 3 combined. Physicists move one step closer to a theoretical showdown. So that's the controversy I talked about. Since the theory number isn't clear yet where it's going to land up, there are like measurements going into the theory calculation as well. So it's kind of all over the place. So it's like really exciting times to be doing G-2. But besides that, what I'm most proud of is that Mark Hamill himself tweeted us when we first published the results, saying that there's evidence the force has always been with us. So that's I think more valuable to me than any other Times article. So that's cool. That also like gives you the widespread kind of the impact of this result and the experiment has on the community. It has big impact. Like, since Higgs, this is like one of the biggest things that actually came out of particle physics. That's new and exciting. Okay, so thanks for attending. I will leave you with one last meme for you to ponder on a bit, and thanks for listening to my lecture.
Yeah, let's all thank the speaker. Great talk. How do we want to do this? Do you want to take, well, should we do questions, or should we just let the panel, save the questions for the panel? Do you want to take 5 minutes? Yep. We're going to take 5 minutes to get set up for the panel. People on Zoom, stick around. I guess we'll start around 11:10 to 11:06 right now. We just need to set up some chairs. But yeah, let's thank Mete one more time for the great talk. We'll be back in 5 with 3 panelists that will talk about, this experiment, also the mu-to-e experiment, and the showdown between experiment and theory. So,
all right, is it 11:10 yet? It is 11:10. We're going to get started with our muon panel. So I wanted to have a muon panel this year specifically because muons, as practiced at Fermilab, are the future. Soon, which is coming in, which is going to do some interesting stuff. That is the intensity frontier. We also have some access to LHC through CMS. That is the energy frontier. One of the questions we've been asking in physics in general is, what do we do after? Have you folks been watching YouTube? Anybody heard of Sabine Hossenfelder? Sabine often makes this criticism that as physicists, we don't quite have a plan of what we're going to do after we do our current batch of experiments. We have some arguments. I feel that the muon program has been set up to give us some hints as where we're going in the future. So we wanted to make sure we got some folks in here who knew more about muons than I did to answer some questions. So the first thing we're going to do is have you briefly introduce yourselves.
Wait, hello. My name is Jason Krinkovic. I used to be a postdoc on G-2. I'm currently working with in the accelerator division at Fermilab.
Hi, my name is Dan Ambrose. I'm a physicist on the mu-to-E experiment, helping build the tracker.
Morning. My name is Rodolfo Capdevila. I'm a theorist, and I'm probably the muon collider guy in the third floor, the theory floor.
Oh, I don't need it. You guys need to hold it.
All right.
So we can do this a few different ways. I can ask some questions that I think are interesting and relevant. Or because we skipped the question and answer period of the last talk to make sure we actually got enough time for the panel, we can go through some of those questions first. How does everybody feel in the room? How does everybody feel on Zoom? Is there a ton of questions on Zoom? How does everybody feel in the room? Any burning questions you want to know about muons or muon G-2? Yeah, of course. You guys already know Mate.
When we were looking at the graph of like the expected and predicted values and the standard model and things like that, there was the pink line that was like the expected values, and then there was the measured values. So how did you get the expected values outside of the standard model? Make sense?
I think she's asking how you do standard model calculations to compare to experiment.
Right. So I'm not a theorist, but my thesis actually was motivated by this. So there's a very long history to this. Okay. So one of the things that's nice about it's both a strength and a weakness of G-2 is that it sort of tests all of the standard model. Okay. So it sort of integrates over all the different effects except for gravity because the standard model doesn't really describe gravity. And so you can break this down into different components. So what we call QED is essentially electromagnetism in the standard model. And that's probably the force you're most familiar with. But then you have more exotic forces like the weak force and QCD, which is sometimes called the strong force. Okay. And so it turns out that it's easy to calculate things in the electromagnetic contributions and the weak contributions. It gets very hard to do the QCD contributions or the strong contributions. And so traditionally, what you do is you go out and you do certain measurements that are relevant to the problem, and then the theorists take that data and they turn it into a standard model prediction. Okay, and so that causes all sorts of issues in that right now you're doing experiments for your theory prediction, but you know sort of the current state of the art is to do what they call lattice QCD, and that's more of a direct sort of calculation, but that turns out to be very, very computationally intensive, so it's not trivial to do, and that's an important developing field, getting better at doing that, in time scales that it doesn't take forever to get an answer. So that's really what's going back and forth is how do you interpret these old ways of determining the QCD contribution that's based off of experiments, but people have been doing it for decades, so they're very confident with it, with some of these newer calculation techniques. Since you're a proper theorist, I don't know if you wanted to add anything.
Anybody else want to add a stab? No? Okay. What else we got in the room? On Zoom? Oh, we've got one.
Maybe for Rodolfo, like, so what could this new physics be? Like, if there's what's wrong with the standard model, or why can't the standard model explain what we're seeing in the G-2 experiment? Or there could be extensions to it, or maybe I'm leading the question, but
Pass them back.
oh yeah.
Well, the standard model is very beautiful and it explains much everything we and tested the standard model like multiple ways and on confirming its predictions, right? But there are other things. There are always new things that involve dark matter in the universe, right? So has convinced us dark matter out there. He made hypotheses of what happens if this is new particle, right? New particle is actually interacting with the muon somehow, or with this quantum cloud surrounding the muon, right? Possibilities. So and as well, the other things theory is talking about how the universe, if it was hot and made of particles and antiparticles, why it didn't just collapse into radiation? Why there's more matter than antimatter, right? Theory is explaining that, and in those theories, new particles show up, new interactions. Maybe those are also part of the quantum muon cloud that affects the human. So, you made the hypothesis and then go and look for it. You look for it at colliders, neutrino experiments, where you can.
Anybody else want to take a stab?
Yeah, one of the advantages in G-2 is, as you were saying, it's a very open window, and you have, because you're dealing with the vacuum or interactions, you have a very wide window to see any new particles or anything else that's new out there would be reflected in the measurement done by G-2. But yeah, the matter antimatter asymmetry, dark matter, to some extent there's an inflation period predicted by the Big Bang if we want inflatons, but there's lots of searches for other more exotic particles out there. E prime, a few, they look for dark photons. Yeah, there's a lot of different. Those are some examples of different theories that are in place to explain some of these properties that were mentioned there. And some of if those were true, it's possible that they could be seen in the G-2 measurement.
Anybody else want to take a stab? I have to if you don't want to.
So I'm not sure if I'm adding anything really new, but I think it's just in general, if you're a theorist and you say, okay, I'm coming up with a new model that could lead to some new physics, generally to be taken seriously, you kind of have to go, okay, how does my model affect things we've already measured, right? So, G-2 would be an example of a big, it could be the mass of the Higgs boson or something like that, right? Because if your model says, oh, the Higgs boson's 10 times the mass that we measure it to be, there's a problem, right? So a lot of this is you're a theorist and you come up with your favorite model, and one of the things you can now ask is is it consistent with what we're seeing with this particular measurement? And that, that'll actually be a spectrum of different measurements. We'll do these consistency checks.
Okay. Anything else in the room?
So if muons decay and release positrons, does that mean they're reactive in a way? Radioactive.
Yeah, I would describe it more as they're not stable. They're not a stable particle, just like a radioactive. So for something like that isn't stable and it will eventually decay. Muons, or those higher generations of matter, is inherently not stable, and they will go down to what we call our first generation of matter, or some of the stable ones. So an electron and a positron are examples of the stable charged leptons, but your mu plus, mu minus as a second generation, or the tau, they have lifetimes. The muon, for example, only lives for 2.2 milliseconds, microseconds. Thank you. Yeah, and the tau is 7 orders of magnitude higher than that, like I think 2 times 10 to the negative 13 seconds. So that is an incredibly small amount of time, and that just has to do with they're massive and unstable particles.
I would ask. Oh, go ahead.
Something beautiful is the same force that induces the active material to decay, and the muon to decay is the weak nuclear force.
I was literally about to say something similar. No, which is that all of it's kind of like radioactive decay because it's the same force. Turns out, thinking about radioactivity allowed us to open up the entire world of particle physics. Other questions?
So if a muon is better than an electron, or when it comes to like getting these measurements, and I'm assuming the tau would be even better if it was possible to use it. Is there a way to like extend like the lifetime of these particles usable?
So in principle, yes, but as just mentioned, it's so much shorter than so the muon. So on a normal human scale, 2.2 microseconds is really fast, right? Because micros 10 to the minus 6, right? But when you start building electronics, right, electronics can move fast enough, and so it gives you time to start doing manipulations and things like that. And as Mete explained, when they're moving, at the speeds that we do the experiment with, it gets up to 64.4 microseconds, right, which is even more time to start building beams and manipulating things. And so yeah, it's a yes in principle, but realistically, to get to the energies that you would have to get and produce it, and it's just not practical with our current technology. That doesn't mean you couldn't do it someday, but today we can't do things like that.
All right. Oh, we got somebody else. Man, you guys are a serious bunch.
Yes, the one thing that I don't understand is like a muon is a elementary particle, so it can't be broken down into anything smaller. But then at the same time, it decays into positrons, and like I guess I don't understand the process of.
Anybody want to take a stab at that one?
Okay. I think you're kind of getting at sort of the limits of our knowledge, okay? Because even this whole issue of the whole discussion of spin, right? Because one simplistic answer is, oh, well, the muon's is made out of stuff that we're not aware of, and that's what's actually spinning, right? So, does it make physical sense to really have this concept of a, in a mathematical sense, a literal point particle? Probably not. But this is the best we know currently, right? And part of being able to go to higher energies actually allows us to see smaller and smaller distances. That's one way to think about it. So one of our reasons that we want to push up to machines that do higher energies with these collider experiments is that essentially we can see smaller and smaller things. And so the way we can do our models, we treat them as point particles, and sort of you kind of have these magic, they're called Feynman diagrams. And, you kind of think of, two particles collide, they annihilate, they produce another particle, and this is this weird sort of instantaneous sort of process that probably isn't really physically real, but it's just our current knowledge where we're at.
Kind of continuing on that a little, it's difficult to think of when you think of them as point particles splitting into other point particles, but a lot of the interpretation can also be think of it as a wave, and it makes a little bit more sense as a wave if you imagine a resonance of a vacuum. You could split that into smaller other resonances that are still not necessarily, you're not thinking of taking a ball and hitting it with a hammer and then getting smaller balls. It's more of a wave, and from that you excite other resonances in the vacuum. That's
No,
if
no,
you want to
no.
help out.
No.
No. Yeah, that's about what I wanted to say.
I was trying to, on the go, maybe it's not the best way, but like something that is more familiar to you is like a chemical reaction, right? Where you have some element that then you usually have like one or two elements, and then you have an error, and then other elements. Imagine a reaction in which you have only one element, some process, and a lighter element, and let's say heat, right? That's one of the, so the error in chemistry will be some chemical reaction, some process. Here is something physical, something weird that happens where now a heavy particle like the muon, then through a physical process now converts into a electron or positron, and then the heat will be, let's say, neutrinos. That so and you don't detect them unless you build this huge Fermilab experiment. But it's that's sort of like a simul, and we use the same notation of like particle one, particle two, arrow, particle three, particle four. So maybe that's a simul that you can find.
So I'll take a bit because I thought about this a lot. So I think I was here a couple weeks ago. I'm sorry, I've been traveling. But I talked about tuning forks. You guys remember that? What I said about tuning forks? So how many of you play music? Do you play piano? You know that when you want to tune a piano, you have tuning forks of different frequencies. You want your piano string to match your tuning fork. But you also know that if you have two tuning forks and they are similar frequencies, if you hit one, sometimes the other one will feel it and it will spontaneously start vibrating. Right? Anybody else know that? Ever seen that happen? All of space-time is like that. Tuning forks are the different individual fields and particles that are interacting with each other. Sometimes you can have fluctuations in one field, and that can spontaneously generate fluctuations in another field. That is the way in which we mathematically understand decays. Literally just there's some vibration, and that vibration spontaneously starts a vibration in another field. Energy is transferred through that coupling and or through that resonance. Do we have any other questions? No. Okay. And then we're going to switch to some of the deeper questions I wanted to get to. Oh, so we are going to actually hold off on that question because I want to put that in proper context. All right, so this is a question I wanted to ask for the entire panel. This is one of the reasons I wanted to make sure we got a varied panel, right? There are currently two operating, or one's operating, one is being built, two operating muon experiments. There's also a muon collider. What I would like each of you to do is put your experiments within the broader context of a muon program at Fermilab and what that means and what you're trying to do, concentrated effort. I have some understanding, but I don't work on these experiments. So I would like to hear from you guys.
Last words for G-2?
Yeah.
Okay, so I mean, Fermilab muon program actually basically started with G-2. Like prior to that, it was all Tevatron and all these other experiments, which they were really successful and exciting. So they decided to bring down the magnet from Brookhaven to here, and that in itself started like this muon program. So they called it muon campus. And they kind of pitched for like, what else can we do here? And you guys are going to talk about soon. But for G-2, we said we published some results last year. So probably next year we will be publishing the rest of the data. So that will be the whole set. That run 4, 5, and 6. That's the final run. The statistics in that sample is actually larger than what we published so far. So it's going to really skyrocket and shrink down on that error bars, and we'll hit our limits because like when it comes down to like systematics that I talked about, we really went far and beyond to make them like really small and make sure we understand like every single equipment magnetic field depth. So that's coming for G-2 next year. So currently, as of right now, we actually stopped operations. We stopped operations like last year around like summer, and then there's like a summer shutdown in Fermilab for accelerators. So they go and work on the accelerator, this whole accelerator complex that enables the science here. So we shut down the G-2. But the experiment didn't finish. First, we needed to do analysis, but in the meantime, we were also like improving our schematics. That means we go into the ring and we measure a bunch of things. We can still run the magnets, measure the magnetic field, and that kind of like we can run the kickers, we can run the quadrupoles, and we can measure them precisely so that we get like corrections for our like formulas that we use to calculate these things. Anyway, so that's what we were doing last year. So as of right now, that's like almost like winded down. We stopped the magnet. So the magnet is a superconducting magnet. It needs to be cooled down, like usually like liquid helium and liquid nitrogen, right? So and there's always like a cryo operator that watch this thing like 24/7, like every day, all the time. So now that operation is done, and magnet when you stopped cooling, it starts warming up, and now it's almost at like room temperature. But it's not going to be used for a while. So people will take their stuff. They're like, get my calorimeter back. I need it. I can sell it on eBay. So people will get their stuff back. We will be left with a magnet that could be used in the future for future experiments. However, one thing you should know about magnets is that they do have like limited lifetime. So we have these things called quenches. So whenever it conducts it conducts a current, right? But sometimes just there's a problem with the magnet, and it's just the specific region it conducts more current. It just that makes everything called quench, and you have to kind of recover from that. That like usually doesn't destroy the magnet, but it could like create some like mechanical damage like inside, like with the coils and everything. But this happened a lot, like people couldn't stop dropping their car keys onto the magnet. So that kind of limits the lifetime of the magnet. So we won't know. Like if we build an experiment for the future future experiment that uses this magnet, and it may not work out really well. It could die, but we really don't know. Maybe that's one thing to like. Maybe you could do an experiment to just study the magnets. That would be actually like really useful for going forward. You have this like really used magnet. You can just study it and understand what happens. So that's my story for G-minus.
Okay, so currently I'm actually part of supporting the neutrino program, but I'll hop around a few things because accelerator division's obviously interested in new experiments because you got to start with accelerator division to do a particle physics experiment at the lab usually. So I know there's a small group of people actually thinking about doing what they call muon EDM measurement. So it's kind of like the equivalent of G-2, except you're looking at the electric version of it, which you don't really expect to see from some standard model physics. So if you observe something, that would automatically tell you there's some new physics. So there's people working on, how would you modify the ring system to do a much better version of it. Actually, G-2 can also measure, basically do this measurement in the data set, but they're thinking about, stepping back and going, how would you do something like 10 times better than what the current experiment could do? That's one thing. Another thing, a big thing on the horizon, which actually probably would be on your time scale. So if you're interested in making a career in particle physics, it's probably the muon collider. The reason the time scales are going to be very, very long is it involves a lot of R&D, which is expensive. It also, you're talking, this is not a small thing, right? I mean, there's one experimental hall. You can put G-2 in, and the grand scheme, it's not big, but you're talking about, people are dreaming of building a ring that's essentially the size of Fermilab itself. Okay, so there's a lot of civil engineering and a lot of practical stuff to make it work, and so we don't want to waste money, right? And so a lot of thought gets put into what do we really want to design, what do we really want to do, and the question is well, why build a muon collider? Because again, right, you have these particles, they decay, it's kind of hard, but you would do it at very high energies, which means you would get, the lifetime would be dilated to something, much larger than the 2.2 microseconds, and it would, let you do these, beams on these larger scales, and so, so sort of the motivation. How do I want to say this? So there's sort of been, so a collider, the goal is to kind of go as high energy as you can, typically, okay, right? And so, first when particle physics was young, right, you get some particles and you get them moving with a relatively simple device, and then you smack it into just a chunk of stuff, right? And we call that fixed target, okay? And that gets you so far because eventually you sort of run into technology limitations on how far you can accelerate your stuff. And then we eventually learned, well, if you take two beams and you smack them into each other, right, opposite directions going into each other, well, that helps you go to higher energies, okay? And so then, the next thing is, or I should say equivalent energy, to be clear. So there's actual energies and there's sort of equivalent energies. And because you have to remember, particle physics is a statistics game, okay? It's about getting kind of as much data as you can, and then you data mine it and you try to understand it. And the more data you have, the more things you can understand, okay? And so part of this is, right now, sort of the high energy state of the art is with protons, okay? And protons really are a messy bag of particles, okay? And so, you get these messier collisions, okay? And so it would be nice if you use particles that, we view as point particles, which would be muons, okay? Now, a simple question is, why don't you just use electrons, right? Because they're stable, in practice, that makes things simpler. The problem is, there's sort of two ways you do this, okay? You either take up a whole bunch of land and you basically just create a completely straight accelerator, okay? But again, it's going to be expensive because you have to use a whole bunch of land to do this, right? And then you have to instrument all that and you have to, make it all work over a very long distance. And so basically the electrons are, mostly, they're just going into a straight line. And what happens is when you accelerate an electron, it wants to emit off radiation, right, which costs you energy. Okay, and so from a practical point of view, it's better to have a ring because you need less space to do that, right? Which means you spend less money to do it. But you have to remember that acceleration is really changing velocity. So there's two kinds of acceleration, right? You're changing the speed. That's one kind of acceleration. You're just changing the direction of the particle, the velocity. That's another kind, right? So in a ring, you're always changing direction, right? So when you do it with electrons, very quickly you start radiating away a whole bunch of energy. Okay, and that becomes, again, expensive. But since the muons are a lot heavier, they're about 200 times heavier than an electron, you end up radiating a lot less energy away. Plus, then it has the advantage of, we view it currently as a point particle, not as a messy bag of quarks, like a proton. And so really what happens is sort of what people are dreaming for at the moment is what they call a 10 TeV machine. Okay, so an EV is the amount of energy an electron gets going through 1 volt, right? So if you could set up little tiny accelerator with a 9-volt battery, you'd have 9 electron volts by just taking an electron, right, accelerating it that way, right? But the state of the art now is for particle physics in practice, it begins at millions of electron volts. Typically we're at billions or hundreds of billions of electron volts. At CERN, they're doing TeV, so 14 TeV, so that's trillions of electron volts, right? And so right now, sort of people are dreaming for a muon collider, 10 TeV, which of course is actually less than 14 TeV, but since it's a point particle, you're going to get a lot more interesting interactions out of it, because you're colliding together simpler objects. Because what happens in practice is the proton, if it's made up of a bunch of stuff, what's really happening is the stuff inside the protons are what really are colliding, that are producing the particles that you're measuring. They only have a fraction of the energy and momentum of the whole proton itself, and so that's why it's effectively less. Right, and so I think the number I saw recently was like 7 times. So that would be sort of equivalent to, if you had a 10 TeV muon collider, that'd be like a 70 TeV proton collider. Okay, and again, you have to remember, accelerator science really it's a practical science. It's a lot of technological limitations, and it's harder to build magnets that have higher fields, right? As you make a ring bigger, there's practical things like, you have to sometimes know where something's down to a millimeter or something like that, right? Well, if you build, a ring that's miles and miles long, it gets really hard to understand where all your parts are down to like a millimeter, right? So the smaller, the better, basically. So then the last thing I would comment, actually, I don't think it gets much press, but there is work on a low energy muon beam at the lab. It's mostly finished. There's a little bit more to do. This, is on the opposite end, so I think they're hoping to get muons down to 30 MeV. And so you can do different kinds of experiments. I think their flagship experiment for this beamline actually is looking at what's called muon catalyzed fusion. Okay, and so this is sort of an interesting mix of particle physics and chemistry, where if you take a regular electron out of a hydrogen atom and you replace it with a muon, it kind of shrinks the scale of the atom and the molecule down, because the muon's, again, about 200 times heavier than the electron. So if you use these heavier isotopes of hydrogen, deuterium has an extra neutron. So regular hydrogen is just a proton. Deuterium has a proton and a neutron, and tritium has a proton and 2 neutrons. So you can kind of get this thing where everything gets close enough together, and these heavier isotopes of hydrogen will then fuse together, right? And of course, the ultimate dream is, can you get useful energy out of this? And it turns into this practical game of you have to reuse the, because again, it's energy intensive to produce muons, but if you can get them to cause enough fusions before it decays away, then in principle you could have a net benefit. And so this was interesting in the past. It was just one of those things where you can never kind of get the more energy out than you put in, but these effects and how it works is dependent both on the temperature and the pressure of the gas. And so that's what this latest round of experiments wants to do, is look at essentially the physics of this as a function of temperature and pressure.
Okay. So my work is in mu to E, and that's one of the next big experiments that's going to take place on the muon campus here at Fermilab. So a very brief description of this is we're looking for muon to electron conversion. And so as being described with a bunch of these, instead of the muon decaying into 2 neutrinos and a electron, you don't have the neutrinos. And how you get away with this is we end up stopping the muon so that it becomes part of a muonic atom. We're using aluminum as our target, and we form this muonic atom where the muon takes the place of an electron, effectively orbiting here. And so it can, when it does that, because it's so much more massive, it's much closer to the nucleus, and it's much more likely to interact with the nucleus. And so what we have, it can interact with the nucleus, and that way you can conserve momentum. Because one of the reasons you can never have a heavier object decay into a smaller object is you can't, or a single smaller object, is it can't conserve momentum. You can't shift into a reference frame where that energy goes into momentum, and it, you would usually need 2 particles in order to conserve the momentum. So in this decay, we have muonic atom, and we're looking for it to effectively rebound off of the aluminum nucleus, and this allows all the energy to go into the muon, so we get the 105 MeV electron as our signal. So this is very exciting. Since the muon was first discovered 80-some years ago, I think, at this point, the initial thought was, oh, this is just a excited electron. You would expect it to be able to give off some of its energy as a gamma, and then you have an electron left over.
Gamma is a photon.
Yes, thank you. Gamma ray as a photon. However, this wasn't seen, but that hasn't stopped us from looking. And so there's been a bunch of these searches for muon. So you have your mu to E gamma, electron and photon, or mu to 3E, which is very similar. This would be 1 positron, 2 electrons if you're mu minus. But you could get that also through the gamma. You have your E equals mc squared. You can split. You can form E plus E minus from a photon to get that. Or in our case, we The conversion allows a lot of different interactions. It interacts with the nucleus, but we leave the window very open on what that could be. So mu to E is exciting, and it's going to be hopefully starting up in the next couple years here. We're moving all the stuff to the building. So there's a new mu to E building on the Muon campus here, and the magnets are getting moved over now. We're working on the tracker, and that's hopefully coming over at the end of the year. Then we have to do some commissioning, but this experiment will take place. And one of the real exciting things about this is it's 4 orders of magnitude more precise than anything else that's been done before. So the previous experiment has a measurement that says this doesn't happen, the mu to E conversion doesn't happen at a rate of 10 to the negative 13. So if we had 10 to the 13 muons in this situation, we wouldn't expect to see one of them, roughly speaking, decay this way. Now, we're 4 orders of magnitude higher, so that means out of 10 to the 17. So when we're running this experiment, which will last multiple years, there is a shutdown that's happening in the middle of our experiment to improve the PIP2 accelerator. But if we do our full run, which will be probably 4 or so years, we expect to stop 10 to the 18 muons. So this process happens when we're running, there's 10 billion muons that get stopped a second. And you go over the course of 4 years or so, and then we're able to hit our mark where we can push the event sensitivity, the likelihood of seeing this at 10 to the negative 17. So mu to E is very exciting in that because these 4 orders of magnitude give us an opportunity to see things beyond the standard model that you wouldn't otherwise see. So there's mu to E, so what I'm describing here is with an aluminum nucleus, but you can change the material you're stopping on, and that also allows for an expansion of testing different models. So that's happening. At the same time, that's competing, but we have effectively a similar experiment that's happening in J-Park in Japan. It's called COMET, which is also a mu to E conversion experiment that's happening in kind of the same time frame. Beyond mu to E, there's an improvement to improve the sensitivity there. We're looking at mu to E2, where we have even another order of magnitude increase. And then there's been talk of the advanced muon facility, which you described a little bit there. There could be a muon storage ring and the design there. So this is, 2040, like this is in the future a ways here. If that ends up getting made, and that can lead the way to a muon accelerator, as you described, because there's a lot of advantages of making a Higgs factory, something that is tuned. So whereas in the hadron, as he was describing, it's very messy. They hit together. You don't know how fast each constituent is moving reference to each other when they run into each other. So you don't know what the center of mass energy is of what hit together. But muons, if they're point particles, if they're hitting each other, you know the energy of both of them hit. And so then you have a lot of information of if you're missing anything, so they hit together and you don't reconstruct things, you make the statement, well, this missing energy is either, it could be a new particle, it could be neutrinos, which you don't usually measure there. So you have a lot of advantages. And it's considered much cleaner because you know what the center of mass energy is and you can tune them to specific resonances. So we could tune it so that you're effectively making a bunch of Higgses, and then you can study exactly what that is. So that's a field where muons could be very exciting.
So like motivations for the future colliders is, for example, so we have the LHC and we produce the Higgs. So we discovered the Higgs. We've been measuring its properties. So how does it interact with other particles? How does it decay? So far, the predictions matches the standard model very well. But we want the next collider to produce a lot of Higgses so we can study it more precisely. And Higgs could be the portal that opens up us, or it's like the force that communicates to something new, something crazy. Right? There are many theories for that. But also, remember, so early last century, we only knew the proton, the electron, the neutron. At some point in history, we reached colliders with enough energy, and a proliferation of particles came out. We discovered so many particles because of this thing called the QED, the quantum chromodynamic, the strong force scale that where many particles show up. So there are theories that predicted the same for the LHC, for the Large Hadron Collider. So we were going to discover new particles related to something called supersymmetry or other theories, right? So the consensus is that we want to get to the highest energy possible because these new particles are going to show up. Many theories. I mentioned to you the matter antimatter asymmetry. I mentioned to you dark matter, but there are many theories. So the muon collider is the one that promises the two. We can produce a lot of Higgses, so we can study it. Well, we can reach very, very high energies, so we can produce these new crazy particles that are out there.
So I'll come in a bit. So I wanted you guys to talk about your individual experiments because I don't know if you realize that the powers that be, the director, the former director, and the current director have sort of arranged the muon program for a specific purpose. And I don't know if they talked about that purpose. Something that I see that seems obvious to me if you step back and take a look at it. So muon G-2 was bought, right? And its job was to probe whether there was interesting physics to look for in the standard model, right? There was a measurement being made, and there was a question of, is there a difference between what we measure and what the standard model says? The answer, it seems so far, was yes, right? The next step of that program would be to go to mu to E and says, okay, if there is a difference, where is that difference? Find that difference by using different, I guess would be atoms. You would do the stopping, and that would allow you to probe different ranges of energy, so you could get a rough calculation where you should be looking for new physics. And then in the process of developing these two experiments, you learn enough about muons such that you can make a muon collider. Now you know at which energy that muon collider should be because the two experiments before it told you where it should be. So there has been a question on the internet, at least since I've been thinking about it, where is particle physics going next? This set of experiments tells you where it's going next. You have to do the experiments to figure that out. But I sort of think that's really interesting. I don't think most people outside of the field of muons really talks about it. Maybe you guys need better publicists. I also have my own selfish interest in the muon collider, because it turns out when you make a lot of muons, you also make a lot of neutrinos. So we can make a muon collider. We can make a high energy, high intensity neutrino beam. Really interesting stuff with, like possibly look for more things about oscillation, which we'll learn about. But I have an interest in using neutrinos for the structure of nuclear physics. So this bag of particles that protons are, it turns out we don't know a lot about that. And if we build a muon collider and sort of backdoor Fermilab into being a laboratory that does nuclear physics as well as it does particle physics. So what some of the things I'm interested in. So I hope that picture came through. You guys are interested in trying to figure out where we're going in particle physics. These experiments are very exciting, and I wish you guys talked more about it. So with that being said, we got 4 minutes left. Anybody got any pressing questions? You guys want to know? Not? Oh.
So your question was not, it was crazy, but not totally. Like when you mentioned the possibility of enlarging the lifetime of tau.
Yeah.
I've been doing a calculation where you put a muon on a very intense field. Uh, the new lasers, where they take a laser pulse and they get intensity of the electric field is very big. I'm trying to see what happens if the muon in that environment could live longer. Because like the muon, the reaction is that the muon goes to electron and neutrinos, but then in that environment, the electron will have too much energy. Like, think about potential energy, right? Then the muon would not be as heavy enough to decay to the muon, to the electron. The electron is like, has too much potential energy. So it's like, it's too heavy. But so far my calculation is not telling me anything.
Life of a theorist, huh?
Yeah. So it might be just a crazy thing, or it could be really something. I don't know.
All right, folks, let's thank our panelists. Thanks for dropping by. All right. I think we got something next week. What's next? Sorry? I mean, for the talk. Huh. You guys can look it up online. I don't remember which one it is next week, but hope to see you next week. I probably will be out of town. I have to talk at a university about the science that I do. So you guys haven't seen me a lot this semester already. Promise I'll be around a lot after next week. All right, y'all. See you in a couple weeks.